Okay, so hi everyone, thanks for joining. So today, Abhinav Verma is going to be talking about some of his work on program synthesis for machine learning. He's a PhD student at UT Austin working with Swarat Chowdhury, and he's been doing some great work on programmatically uh, interpretable reinforcement learning and other topics in that area. So yeah, I'll hand it over to you, Abhinav. Uh, yeah.
Thanks, Osbert. Yeah, I'll be talking about programmatic reinforcement learning today. And before we jump into what programmatic reinforcement learning is, just a quick few words about why we're talking about reinforcement learning in general. It's because reinforcement learning has, of course, made massive strides in the world of playing games, but it's also now entering the real world in the sense that people are using it for tasks in which it will interact with humans or has potential for really causing harm if things go wrong. So for example, here on the left, you have a car that's being trained through reinforcement learning and driving on a safe track, some protein for folding being discovered through reinforcement learning, and then robotics applications in which robots actually help humans perform complicated tasks which have serious consequences. So the main challenge that we want to tackle is that we want the performance benefits of reinforcement learning, but with reliability and accountability built in. So we don't want to really lose out on the scope and performance, but we do want to be able to say that this is going to work. And if it doesn't work, we want to be able to figure out why it's not working and fix that. Before we jump into like the definition of reinforcement of programmatic reinforcement learning, a quick refresher about what reinforcement learning is and what we mean by it when we talk about it, because there are a few flavors. But at the highest level, it's just this loop that is an environment and an agent. And so you abstracted these two things into separate blocks. And the environment gives the agent a state. And based on that state, the agent acts and gives basically gives that action to the environment. And so the state changes. And based on that action also, the agent gets a reward. And this loop is often formalized as a Markov decision process. But the goal is usually to find a policy, which just means it's a stochastic map from states to actions. And that means that that's how the agent basically decides what to do when it looks at a state. So if you give me a state, I have a function to tell me what action I want to take. And the goal across reinforcement learning is to find an optimal policy with respect to the reward. By this, we just mean that if you use that policy to interact with the environment, some notion of the discounted aggregate reward will be maximized in expectation, which is what that equation is capturing at the bottom. And one of the areas where there's been tremendous growth and interest is deep reinforcement learning. And this is really just reinforcement learning, where that policy, which is just, remember, a function, it's just a map usually, but you think of it as a function, that policy is represented by a neural network. So neural networks are universal function approximators. So you can just stick in a neural network there and ask it to learn a good function that actually maximizes that aggregate reward. And so when you stick in a neural network, because these neural networks are differentiable and they can use gradient-based learning methods, they leverage that to optimize for a good policy and end up learning very good policies in certain tasks and achieve the state-of-the-art performance across many of these challenging tasks that reinforcement learning people have been looking at. So the idea here is simply that deep reinforcement learning is just reinforcement learning where the policy is represented by a neural network. And this is great. And if all we care about is performance, then maybe this might be enough. We might just need to look at larger and larger neural networks. But there are certain challenges inherent to deep reinforcement learning, which we want to look at and tackle. So the first challenge is that neural networks are black box policy representations. So they are hard to understand. They're basically uninterpretable. You have ways people looking at explainability of neural networks, where sort of they can explain local actions. But inherently, a large neural network is hard to understand. You can't look at the weights and nodes and understand why it's taking the decisions it's taking. And because of that, it's hard to trust or debug. The other issue is that neural networks have issues with large variance occurring during learning. So there is sort of missing inherent regularization in them, especially domain-specific regularization. And that's why people have shown that the same training algorithm, depending on the random seed, can generate wildly different results. And so this makes learning with neural networks inherently unreliable. The next issue that we want to talk about is how they're hard to verify, which means that we want to give formal guarantees like we do in software verification. So these are machine-generated guarantees about certain desirable behavior. But neural networks, because they're low level, so they typically represent the policies with very large parameter sets and large networks. So they're hard to verify. And again, I do want to mention that there is a branch of research looking into verifying neural networks directly, but it's a challenging task and inherently very computationally expensive just because of their low-level structure and because of that, because they have so many parameters. And the final problem we want to talk about is how they have domain ignorance, which is basically, it's very hard to tell them give them any prior information about the world that they'll be working in. So you can't really easily programmatically change their inductive bias. And because of this, they have to learn everything end to end, which is great if that's what you want to do. But often in challenging tasks, you need to give a learner some information about the domain, and that usually speeds up learning even in other cases. And it's very useful because without that, sometimes even the best deep RL methods don't find a competitive policy. So it's hard or impossible to give programmatic knowledge about the domain to the neural network. And all of these issues, so some people are looking at how you could pre-train it on related tasks and then maybe use transfer learning or things like that to sort of influence, give some domain-specific guidance before the actual training of the neural network begins on a particular task. But the main issue here is that all of these are very challenging issues which create an inherent problem with using these black box policies. And we want to address them all together. All four of them need to be tackled together, and we'll be calling these the four horsemen of the deep learning apocalypse. And while each individual piece has been tackled separately by various methods, we believe that programmatic reinforcement learning is a principal mechanism to tackle all four together. So just to ground this in terms of an example, this is our sort of running environment. It's the open racing car simulator. You're trying to drive a car around a track, and your aim is just to complete the track as fast as possible. You're looking at certain sensor values while driving this car, and you're giving it actions which are depicted on the bottom right. And this is the performance on a training track for DDPG after some amount of training. The impressive thing here is, again, that it's learned this completely from scratch. It has no idea it's driving a car. It has no idea what the track is. It just learns from the reward what it needs to do, and it completes the track. And this is exciting. If this is what we wanted to do, we now feel that, okay, we've learned how to drive. But as we talked about this, as we mentioned, there are issues. And one of the first issues we'll see is that there's some amount of memorization going on, because if we change the track slightly, we'll see things will go bad. And this is not a much harder track. It's in fact very similar. It's just got different turns, but it's roughly the same width most of the time and things like that. And then we see that the trained policy suddenly hits a wall and tries to drive through that wall. It doesn't even stop. So these are the kind of problems that we want to tackle, because if you see this, now you are stuck because you don't really know why it's doing that. You can't interpret its decisions. You can't debug those decisions. You didn't have any guarantees about it not behaving like that. And you can't give it information about the world so that it maybe understands a wall and never crashes into a wall. So a quick outline about what this talk is going to cover. We are going to talk about the programmatic reinforcement learning framework. Then we'll cover neurosymbolic learning techniques for programmatic reinforcement learning. And then we'll talk about programmatic learning being used in SafeRL in recent work. So we talked about what deep reinforcement learning is. It's just the policy being represented by a giant neural network. And similarly, in programmatic reinforcement learning, the idea is the same. You have to represent your policy in a certain manner. But now we are giving this extra constraint that we are going to have the user specify a policy language. This is usually just a programming domain-specific language, typically given as a CFG, a context-free grammar. And the idea here is simply that now this function has to be representable in a program from this language. So the optimization goal is the same. It's just constrained so that now you're trying to find a policy pi, which is within that program, which is a program in that domain-specific language. But the goal is still to find a program that's maximizing the aggregate reward. So now we've given it a specific domain-specific language, and we wanted to find a program within that domain-specific language. So, for example, if you just gave a domain-specific language that gave you access to all neural architectures, this is in some sense AutoML. So we won't be talking about that. We'll look at domain-specific languages which are interpretable and give environment information. But this is a general enough definition that it actually captures various sort of paradigms of policy search. So if you give it a language which specifically uses just a particular neural network, then this is literally just deep learning, because you're trying to find that particular network parameters that maximize this reward. But in general, you can give it any domain-specific language, and we'll be giving it domain-specific languages that are interesting for a particular domain which use certain primitives. So just to use the input-output view of things, remember what we mentioned was that a policy is nothing but a map from states to actions. And in deep reinforcement learning, or in reinforcement learning in general, you're using data to learn that policy. In deep reinforcement learning, that policy is represented by a neural network. But basically, there's a learner, it takes in data, which is just state, action, reward tuples, and then learns a policy, which is a map from states to actions. And in programmatic policy learning, we give it one extra piece of information, which is a domain-specific language. And then we learn a policy, but that policy is represented as a program in that domain-specific language. And it's still just a map from S to A. With that, I'll stop here for a few minutes. Well, not for a few minutes, but I'll stop for a few questions, if there are any.
If anyone has questions, they can type it in the chat. That might be the easiest thing to do, and I can ask them.
Okay. All right, I'll proceed then. So the high-level idea once again here is that you want to find a policy in which is represented as a program in a domain-specific language. And just to give a bit more intuition behind that, a domain-specific language could be given as a CFG, like on the left here. So this language is saying that we are looking for a map, which takes, so it's the pi is a map which takes in the current state, and then it either gives an action, or it gives some other a combination of policies, or an if then else with policies, actions at the nodes and things like that. And the key sort of insight here is, because we're giving this information as a CFG, we can also give predefined controllers which capture domain-specific expertise to this learner in this manner. So this is a principal mechanism of giving information that's useful in a particular task to the policy learner, because we can give this and then the learner can decide if it wants to use it or not, but it has access to these predefined high-level controllers, which would be hard to find directly, and in some cases might even be intractable to search through all possible controllers. So in the case of the car, one of the controllers that we give the policy learner is a PID controller, and the kind of policy it generates is to the right here. And the idea here is that these are the kinds of policies that you would write if you were trying to solve this task yourself. So these are inherently interpretable because the domain-specific language forces this syntactic constraint onto the learner. And just looking at this policy, we might not know what everything means, but you can guess that the first thing that's happening is that the if condition is checking if the car is within a certain band of the track position. So basically, it's checking whether it's in the center of the track. And if it is, then it's speeding up, otherwise it's slowing down. So the main sort of takeaway here is that by giving access to high-level primitives, the policy learner is able to learn parsimonious policies which still perform well. And we'll talk about how it goes about learning this later, but the primary sort of motivation here is that if we have a way to generate policies that are in high-level languages, then we get various benefits. And just to go back to those 4 horsemen, what are the benefits that we are getting? The first one is now these are by default, by design rather, you can give it a domain-specific language that generates interpretable high-level programs. So these are easier to interpret and debug. So you can read the policy and actually understand the logic behind the actions and why it's taking those actions. It's because of the abstractions, the policies are represented in a more compact manner. And so verification is simpler using current program verification tools. The domain-specific primitives actually work as a regularizer, and they show proofs and results to show that they actually reduce variance over the learner's entire episodes. And finally, because once again, that the way giving the primitives in a domain-specific language provide a principal way to give common sense knowledge to the learner. So the programmatic RL framework is just is the idea that we are trying to find a policy in a domain-specific language, but that would be great if it was easy. And we mentioned that deep neural networks have sort of taken over reinforcement learning primarily because they can really leverage gradient-based methods to learn policies efficiently. So how do we go about learning optimal programmatic policies efficiently? And once again, what are the challenges here? The main challenge is that these programs might not be differentiable end-to-end. So you can give, for reasonable tasks, you have to give an expressive enough domain-specific language, which defines a vast and typically non-smooth policy space. So you can't just end-to-end differentiate it and learn parameters or learn structure by that mechanism. In interesting reinforcement learning tasks, you typically have a very long horizon. So the objective might not be met over many learning terms. So it's not easy to evaluate programs, even if you can generate them quick enough. And because of these reasons, direct policy search is typically intractable for interesting tasks and reasonable domain-specific languages. And the key insight that we have here is that we are going to actually leverage neural networks and their ability to learn policies effectively, and then use those neural networks to co-learn programs and neural policies. So we are going to basically use neurosymbolic policies to learn programmatic policies efficiently. So before we talk about how we actually use neurosymbolic policies to learn the programmatic policies, let's quickly talk about what are the kinds of neurosymbolic policies we'll be looking at. So we are looking at basically this blended policy. It's just a linear combination of a neural network on the left and a programmatic policy on the right. And the idea here is that this creates a policy which is both programmatic and neural in nature, because it has components from both. This is just one way of creating a neurosymbolic policy. We'll talk about another towards the end of this talk, but there are many ways of creating neurosymbolic policies, and but for most of this talk we'll be focusing on creating a neurosymbolic policy by taking a linear combination of a neural policy and a symbolic policy. And
sorry, a quick clarifying question.
Yes.
Are you assuming continuous actions here? Is that why you can add them?
Yes.
Okay.
So we are assuming continuous state and action spaces. The continuous state space is not absolutely required immediately, but underlying some of the theoretical results later, it is required, but definitely continuous action spaces. So there, we don't just take a simple linear combination. It's a regular. It has a regularization constant to weight. So it's basically a weighted. So you can think of this as a weighted average of the neural and the programmatic policy. And this already has some benefits. The main benefit is that if you look at if you use a programmatic policy, which is a control prior from control theory perspectives, then you can actually see that this. The way you change the regularization constant actually either increases your bias or increases your variance. So basically, think of this as creating a space in the policy search space where you have a control prior, and you're only allowed to search within a sort of cone around that control prior. So changing that regularization constant changes how much you can search around that control prior. One of the advantages of this kind of neurosymbolic policy is that it reduces variance considerably, because so over here, right now we're thinking of a fixed control prior as the programmatic policy. And that control prior basically makes you behave in a reasonable way for most of the training time. So on the left here, we have a result from the literature, which shows that if on something like cartpole, which is a simple reinforcement learning task, you can, well, it's a control theoretic task, but basically if you run the same algorithm 10 times, you can be in a situation where 7 times you learn a very good policy, but 3 times you learn nothing. And this level of variance is of course very alarming. And then there are obviously many ways to try and tackle this, but one way is to use a control prior to sort of control the variance. And what we show in a paper at ICML 2019 is that using very simple control priors that are not really performant on their own, you can create policies that are still performant, but also with almost with negligible amounts of variance. The issues, especially if you change the regularization constant with a learning term. So these are this is sort of an advantage of a blended policy that we already know of. And now we want to say that, all right, it's great if you have a control prior, but what if you don't have a control prior? How can we go, or even if you have a very simple control prior, can we maybe improve it to get a good programmatic policy at the end? And the key idea here is that, as we talked about programmatic policies are just a constrained form of reinforcement learning. Remember, we are still trying to optimize the same objective as any other reinforcement learning algorithm, but now we had that extra constraint, which was that the policy has to be representable in the programmatic language. And that sort of inspires us to use constrained optimization techniques. So we've created this world of blended policies or neurosymbolic policies in the previous slide. And now what we want to do is we want to find a policy within this neurosymbolic space, which has a purely programmatic representation. So in some sense, we want the neural part's contribution to be 0. So we are going to look at this space of neurosymbolic policies, which can be represented as a sum of neural policies and programmatic policies. The neural should be pointing to the pi. But the key sort of insight here is that we can, through these neurosymbolic policies, we can leverage gradient-based learning techniques to find good programmatic policies as well. And before we sort of jump in on how we do that, we'll quickly talk about mirror ascent, which is a standard technique in constraint optimization. The idea here is that you have an giant unconstrained space, and you have some constraint within that unconstrained space. And you want to find a point in the constraint space that maximizes some kind of objective function. And what mirror ascent shows is that if you take update steps in the unconstrained space and then project that updated point back into the constraint space and do this repeatedly, then you can actually find good approximations for that constraint point, which optimizes your objective function. And one of the sort of key results from the theory around mirror ascent is that if you do this sort of in this mirror-like manner, where you take an update step and you then project, and an update step and then project, you'll actually do better than if you try to just do it in one shot, which would be if you try to just update it to the best possible unconstrained point and then project it to a constraint point. So you have better theoretical guarantees if you do it step by step instead of in one shot. So that inspired us to try and do this in our setting, where our constraint space, remember, is just the space of programmatic policies. That is neurosymbolic policies where you don't have a neural component. And the unconstrained space is linear combinations of neural policies and programmatic policies. So that's what we have on the left here. And that's initially, you just take a randomly initialized neural network as your neural policy, and you'll take a programmatic policy. And again, it can be something as simple as doing nothing, or it could be a simple control prior. But the idea here is that it's not a performant programmatic policy, and you want a performant programmatic policy ultimately. So you first create basically an unconstrained policy from these components, and then you update. And we know how to do updates because you can just simply update the neural part of this neurosymbolic policy. So using any existing deep RL method, you can update the neural policy while keeping the programmatic policy part of this combination fixed. And then after a sufficient number of update steps, you basically project to the programmatic space. So a key point here is we've not talked about how to do this projection yet, but if you sort of assume that there is some way to project a blended policy into onto a programmatic policy, this basically gives us a way to do the mirror ascent technique repeatedly. So you basically project, you create a lifted version of that projected policy where you create another, you just combine it with another randomly initialized neural network, and you follow the same process again. And after a certain number of iterations of this, you'd either converge or you can do it for a fixed threshold number of steps, a computational budget. And the key idea here is that this mechanism gives you a principal way to generate these programmatic policies that are still performant and are using the neural network to learn effectively. So there are the three sort of steps here. You're lifting to create a neurosymbolic policy. You're updating using gradient-based methods, updating only the neural component, and then you're projecting by finding the closest symbolic program to that blended policy. And we'll be talking about how we sort of do the blending next. But just at a high level, there are basically various ways that people have been looking at how to find a programmatic policy, how to sort of distill a programmatic policy given a certain neural policy. And the three ways that I'd like to mention here is NDPS, which is the method we'll talk about in more detail shortly. We have Viper, which is from Osbert and I believe Armando. And then we have another mechanism which is called NEAR, which we are actually adapting currently, which was published at NeurIPS this year. So
quickly, there's a question. What are the required properties of the projection step in the optimization landscape for mirror descent to work?
So the key property is that your projection error should be bounded. So we have some, so basically, if you just want to use the mechanism, of course, you don't have to have too many assumptions, but for the theoretical guarantees to hold, you assume, so there's a convexity assumption on the constraint space, and that the projection error is bounded. So if the projection error is not bounded, basically all bets are off, because for example, your projection could just be taking everything to zero, no action every time. And then of course you'll learn nothing. So if you have some bound on the projection error, we basically give you some, by using one of these projection techniques, we give you guarantees on the regret that you'll have. So you'll have a regret bound. So you're guaranteed to learn something and basically converge to a local, well, a near optimal policy in probability.
So just to when you say projection error, you mean is that the distance that your projection, or like the error compared to some optimal projection?
Error compared to the optimal projection. So
okay, in some metric.
Yes.
Okay.
So basically, the metric is the Bergman divergence, and so if you assume that there is, well, I mean, there is an optimal projected policy, but for our theoretical guarantees to work out, you have to be within a bounded distance of that.
Got it. Thanks.
Thanks. Right. So the key challenge, once again, is how do you find the closest symbolic program? And the key insight here is that we can actually imitate blended policies so that we're not learning, or we're not doing reinforcement learning in the program space from scratch. So we want to be able to use this blended policy, which we believe is finding good points in that policy space. And then we are going to use the information that we've learned here and project that by imitating it using imitation learning. So the key insight is that we can do this because we are removing the problem of exploration, which is really hard if you have a non-smooth policy search space. That exploration is effectively being done by the blended neurosymbolic policy, and then when we are projecting it to the programmatic policy, we are simply imitating that blended policy. So quick word about what imitation learning is. Recall that reinforcement learning diagram. Over here, we're just replacing the agent with an expert. So the claim here is that your expert knows how to deal with your environment very well, but you don't have access to your expert always. So what you want to do is you want to learn a policy which mimics the expert. So whatever the expert actions would have been, you want to learn a policy that would be close to those actions given a particular state. So you want to you've removed the exploration part. You don't want to actually go roam around in the environment trying to find good rewards. You believe your expert's already done that for you. So this is a strictly easier problem setting than RL, because now you're just trying to find a way to copy an existing function that you know performs your task well. And a popular technique for doing this is data aggregation, which is the Dagger framework. And we'll quickly talk about the Dagger framework. So the idea behind Dagger is that you start with an empty set. So basically what we're going to do is we're going to try and copy the performance of the expert on increasingly larger sets of states. So first we'll take an empty set of states and we'll just simulate, we'll just run any policy and generate a bunch of states. So the inherent assumption here is that your expert can label these states for you. So that's one way of doing imitation learning. There are other flavors, but we're assuming that you can give your expert, basically your expert is like an oracle. You can give it a bunch of states and it will tell you what are good, it will label those states by good actions. So it will say, in these states, you should have taken these actions. And so now you have so you generate a bunch of states. Now you have a good set of actions for these states. So you've got basically a supervised learning problem. You've got sets of states as state action pairs. And now you just try and fit a function that best fits the state action pair. So you're trying to find a function that maps these states to these actions. So it's minimizing the distance between your predicted action and the action given by the expert. And once you do this by some particular mechanism, then you can, then basically that's your new policy. And so now you can run your policy again and generate a bunch of states again. And this is a very important step because if you just stopped at this point, you'd face an issue of distributional shift essentially, because now once you have a new policy, you'd actually see states which you've never seen before. And you therefore might not perform that well because you don't have the expert guidance that you needed to do well there. So you're basically taking random actions in completely unseen states initially. So what you want to do is you want to run again, see how how the distribution of states changes, add those states and run this loop a fair number of times. And one of the nice things about this is that it might seem that you might have to do this forever. Theoretically you do, but the idea is as you do it often enough, you approach the optimal policy here being the expert's policy. And in terms of actual practice, you find that this happens reasonably quickly, that you can actually use this mechanism to find good policies which actually imitate the expert reasonably well. And this is what we sort of rely on to do neurally directed program search, which is one of the mechanisms that we mentioned for doing that projection. So now we've applied DeepRL to create this neurosymbolic policy, which we believe is good. So we're going to call that our expert. We're going to use that as an oracle. And we are going to then run the Dagger loop with that oracle. So we are going to start with an empty set. We're going to just take the non-performant programmatic policy and generate a bunch of states, use the neurosymbolic policy to label those states, and then find a function that within the DSL that fits those sets of states and actions. And we do this repeatedly. If we do this repeatedly, Dagger tells us that we'll be able to get a programmatic policy that's very close to the performance or the map that was being represented by the neurosymbolic policy. And sort of the key step here now that remains is that how do we find this good function? Because this function is the key function that has to be in that domain-specific language. And we solve this by doing quantitative program synthesis, which is, and if we can do that, then of course, once we do this often enough, we'll get a programmatic policy on termination. So how do we do quantitative program synthesis is sort of the next thing that we cover. So I'll just stop here again if you have any questions. All right. So how do we do quantitative program synthesis in this situation? So what do we already have? At this stage, we have a set of state and action pairs. So we have this label set, basically, and this is a supervised learning problem. And this is very similar to inductive program synthesis, where you have inputs and outputs. So these are essentially inputs and outputs, but there's a key difference here, which is that you don't have to match them exactly. Because remember, these are continuous state and action pairs. Small changes in actions don't necessarily mean that your policy is completely wrong. So this is a sort of quantitative inductive program synthesis where you're trying to match inputs to outputs, but you're allowing for some error. And the way we solve this program, we solve this problem in NDPS is by doing bottom-up enumerative search in program structure. So let's talk about that first. So recall this is how your program space looks like. It's defined by a CFG. And we're going to do bottom-up enumerative search. So we'll start at the very first sort of workable program, which is given a policy, just give me an action. So if you recall you're driving around, you're trying to find a policy for acceleration. So here are just two actions. So these are two valid policies. The first policy is just accelerate with a certain fixed threshold all the time. And the second policy is don't accelerate, maintain the speed so your acceleration is 0. So you have these two policies, which are just simple actions, primitive actions. And now when you try and fit this to your set of states, you'll probably find that this doesn't work because it doesn't give you a very good answer because, of course, your policy is not likely to be always accelerate or always maintain maintain your speed. So what you do is you try and build this up. So let's look at the next thing that you can look at. So maybe we can combine these two primitive actions into an if-then-else statement. So that's what we try and do next. We try and put an if statement on top of these policies. And the if statement is, all right, let's check if the car is near the track center. And if it is, that means that we're driving somewhat safely. We can try and accelerate right now. And if it's moved away from the center, then maybe you don't want to stop accelerating. So you give 0 acceleration. And that's the kind of mechanism that we can use to build up more and more complex programs and find interesting programs by this mechanism. And a word about, the domain-specific primitives that we were given here, for example, in the car case, it was PID controllers. These can be parameterized functions. And so when we stick in parameterized functions into our built-up program, we'll find good parameters using Bayesian optimization. But you could use other parameter search methods as well, depending on what your primitives are, domain-specific primitives are. So quick word about the results. When we do this mechanism, what we find is if you start your initial deep learning policy might have about 2,000 neurons for that particular domain. You generate trustworthy policies because you can actually understand what they're doing. Again, these are interpretable by design. You can do instantaneous post-learning symbolic verification, which is just that we feed these policies into SAT solvers and generate proofs for desirable properties. For example, you can generate universal bounds for your policies, which could mean that you'll never, for example, violate a speed limit, or your steering won't be too jerky, and things like that. So desirable properties can be verified through scalable symbolic mechanisms. The DSL acts as a regularizer. This is something we mentioned earlier, but just to show that in terms of a picture, these are the steering actions being taken by the deep reinforcement learning agent and the programmatic agent. The orange one is the programmatic agent. So this is on some snapshot of the track. What we see is that the deep learning agent is taking very noisy actions. So this is the steering action. +1 means hard turn to the right, -1 means hard turn to the left. And this is an artifact of the way these agents are trained. The deep reinforcement learning agent is trained with a lot of noise. So for example, when it needs to just go straight, in the mean, it's taking straight actions, but you don't want to sit in this car because essentially the driver is driving like a drunk person, just sticking their steering wheel around left and right. So this is desirable behavior that we can generate because our primitives enforce sort of act as a regularizer for the domain.
So I have a question about that plot, just to make sure I understand. So like usually deep reinforcement learning, the neural network uses, like policy gradient algorithms use added noise to facilitate learning, right? But you could, so is this noise due to that added exploration noise, or is it there even if you say take the most probable action in the neural network?
So once it's been trained, it's taking the most probable action. So the noise is during training. So it's not as if at this point we are adding noise. If you don't add the noise, then typically you won't be able to train the network to a reasonable policy. So can you force the deep reinforcement learning to deep RL algorithm to sort of take more regularized actions? There are mechanisms looking at doing that, but if you just take away the noise, that wouldn't work.
Okay, got it.
Okay, and here's that behavior on the training and testing track once again. So this basically shows what we expect, that you perform reasonably well with respect to the training track, and you don't actually crash so this is the deep RL agent. It's going to crash and when it's moving on an unseen track, whereas the programmatic agent is not. But one of the most exciting parts about this is that because we are doing this regularization and then co-learning the neural and the programmatic policies, we can actually now complete tracks which were too hard for deep reinforcement learning techniques on their own. Because without that regularizing term, without that hidden domain-specific knowledge which is given through the programmatic control part in the neurosymbolic learning, the track was just too hard for deep reinforcement learning to complete. And another nice fact is that this gives us zero-shot generalization, which just means that we can now use the same policy on a different track, and it gives us reasonable performance. Again, it doesn't mean that we can just change the track arbitrarily. In that case, we'd expect and do get a crash. But if you train, for example, on a hard track like Alpine, then you actually are able to finish most other tracks as well. But if you train on an easy track, then you still crash on harder tracks. Whereas the deep reinforcement learning agent crashes a lot more, even if it's trained on harder tracks. So once again, the sort of four horsemen that we wanted to tackle was uninterpretability, which again, by design, we generate high-level programs which are easier to understand and debug. We have smaller programs which are easier to verify. We have programmatic regularization, which reduces variance. And finally, we have a domain-specific language, which gives us a principled way to give common sense knowledge about the world to the learner. And a quick word about the theoretical guarantees that Propel gives us. So the main idea here is that, once again, what you want is that you don't want your errors to sort of accumulate. And in this equation, what we have is we are providing the regret bound. This is with respect to generalized, generic gradient estimates and projection errors. This is with the specific case where your mixed policy is that linear combination that we mentioned and are using. So the regularization constant brings down it reduces the variance, the effect of the variance, but it adds a term, it adds a bias, it adds to the bias of the learner to some extent. The key idea here is that the error and bias do not accumulate over learning runs. They actually just provide an additive error. And again, these are assuming that you have a bounded error, bounded projection error, and then you can use Dagger to actually prove these bounds, because Dagger gives us no regret learning once we have a bounded projection error. And in my last 10 minutes, I'll quickly talk about some recent work where we applied neurosymbolic learning to safe reinforcement, to the task of safe reinforcement learning. So at a high level, the problem here is that you want to be able to use reinforcement learning, but you don't want to make mistakes that are really costly, like crashing your car. So one way to deal with this is shielding. And the idea behind shielding is simply that you have a worst case model of the world. And then using that worst case model, you have a monitor which checks if the action that you're going to take is going to violate some kind of safety primitive. safety specification. If it is going to violate that safety specification, we fall back onto a known safe policy, which is typically a symbolic policy. And if it is not going to violate the safety specification, then we use a neural policy, which we are learning and improving as with each training iteration. So the idea behind shielding is that you have a monitor and a safe policy that you know will not create too much trouble for you. And you are going to use this to constrain the behavior of the neural policy. And then you can basically update your neural policy and learn a better policy over time. But a key sort of drawback of this mechanism is that if your shield is too conservative, you don't do very well. So just to sort of cover that picture once again, what we have here is you have this blue region is your worst case environment model. And it's telling you that it's giving you a way for your monitor to check whether this action AV is going to take you out of the known safe region. And if it is, then you sort of fall back to your invariant preserving safety specification preserving action. And if it is not, then you take the neural action. And we aren't the first people to look at this, of course. Some of the interesting works that we were inspired by were safe reinforcement learning via shielding and an inductive synthesis framework for verifiable learning, which was at AAAI and PLDI, respectively. And once again, what is sort of the key issue that we are trying to deal with here is that if your monitor is too conservative, what do you do? So our solution to this is, well, let's look at neurosymbolic learning, because the idea here is that this is just another way of creating neurosymbolic policies, if you look at it from that lens. So these policies have a symbolic part, which is essentially the monitor and the program, the safe program, and a neural part, which is the neural net. So you can look at this mechanism as simply another way of blending neural and symbolic policies. And once you look at this problem from that lens, the idea of using the Propel framework, basically a mirror ascent framework, to co-learn the shield and the neural policy is an intuitive idea. So what we do here essentially is we look at the safe space. We look at the monitor and the. So the one assumption here is that you have a worst case model of the environment. But once you have that, you look at your monitor and your safe program as one component, and that's your programmatic component. And then you take updates with the neural policy, and project and make your programmatic policy, which is your monitor and safe policy, better. And this helps us maintain safety throughout learning, because when we are updating the neural part, we're keeping the shield fixed. So the shield at that point we know is safe. We are not changing it while we are updating the neural policy. And so each action that we take, even during training, is guaranteed to be safe. So we'll have absolutely no violations of the safety specification. And I just want to mention once again, there are mechanisms of trying to do neural network verification directly, but that's typically very expensive, especially if you're going to try and do it at each update step. So we've avoided that step altogether, because the neural network is not being verified at each update step. While the neural network is being updated, it's basically allowed to do whatever it wants, but the shield is fixed. And then when we do the projection, that's when we use some of these neural network verification techniques to project onto a safe shield. So the update, which is typically, as we all know, when we do deep reinforcement learning, we need to take many neural update steps. And those steps, if we had to verify the neural network at each of those steps, this would be interactive. This is intractable for reasonable domains. So we sidestep that by performing shielded updates and then distilling that knowledge into a better shield. And just a sample result from this technique is this task is to try and follow a car, but safely. So you want to try and accelerate and get very close to the car, but not bang into it. So there's a car in front of you and you're controlling the car right behind it. And what we see here is the trajectory of various trained agents. Well, these have been trained to a certain degree, but for example, CPO, it learns to accelerate very quickly, and then it learns that it's supposed to start braking, but initially it won't brake enough. And that's why it crashes. This red zone is the danger zone where you've crashed into the leading car. But because of the shielding situation, we are able to take that braking action much more sort of with a lot more certainty. And so our learned shield and our static shielded approach both actually do not crash into the into the leading car. But what we show here is also that if you iteratively improve the shield through the propel mechanism, you do better than with a static shield, and you actually perform the task in a more acceptable manner without violating the safety constraint. And so with that, I'll just give the key, sort of re-emphasize our key takeaway here, and that is that programmatic reinforcement learning gives us a principal mechanism to incorporate symbolic knowledge. And this is very important because symbolic knowledge can give you various benefits. It's great to be able to do end-to-end learning for various tasks, but as we move in it, as we try and push reinforcement learning into the real world, we don't want it to learn everything end-to-end by basically trial and error every time. And so we need symbolic knowledge to be incorporated into the learner. And secondly, these mechanisms actually give us a way to do learning more reliably, generate policies that are interpretable, easier to debug, easier to understand, auditable. And finally, they're also verifiable through the well understood and well studied program verification techniques. And so our keys thesis here is that programmatic guidance through these mechanisms provide a path to trustworthy AI. And the future is pretty bright, in my opinion, for this. The idea here is that this gives us a way to leverage the combination of deep reinforcement learning and program synthesis techniques, which give us a rich trove of symbolic knowledge. And there are many conceivable applications, of course. There's assured autonomy, which is what we've been sort of our running example, but there are various other ways in which these things can be put together, not just with reinforcement learning, but with other machine learning paradigms as well. And areas like finance, where you have something like the GDPR, where you can't just take black box actions because people need to be told, and people need to understand those models and audit those models, or data efficient perception, or healthcare. These are various sort of fields where a sort of mix of data-driven discovery through deep learning and symbolic knowledge through program synthesis can be put together to find interpretable and high assurance models. And with that, I'll take any questions. Thank you.
Okay, thanks so much for the talk, Abhinav. Yeah, so if anyone has any questions, you can either just unmute yourself and ask, or type it in the chat and I'll ask it for you. So I guess to get started, I had a question about the last part. I guess it went by a bit quickly. So I was a little confused about where exactly the verification was happening. So are you verifying the neural net at some point? And
the neural net is not being verified directly. What we are doing is we are verifying the projection. So basically, after we've updated the neural network, we are using the neural network to improve our shield. We are using the blended policy to improve our shield. And that needs a sort of a verified projection because that shield has to be safe.
So I guess the question then is like, why, like if you're assuming the neural net can be arbitrary, if I understand correctly, then why would the shield ever change? Because you're always over approximating the neural network as kind of an arbitrary function.
Yes, but the reason the shield would change is because it might be too conservative, and so basically it might be taking actions. So maybe if we go back to this picture here, so essentially there are two components to the shield. One is that it will take some action. So one of the areas of possible improvement, is that you could take a more appropriate action here. So even if you keep the monitor fixed, you can possibly improve your symbolic policy. And the second part is actually improving your monitor, because your monitor has access to this worst case environment model. And so it might basically, it also depends on, its behavior is dependent on your safe policy. So if you've improved your safe policy, you can also improve your monitor. And so basically improving both these things using the neural network can give you a better shielded policy overall.
I see. Okay, so you prove that the monitor might be tailored to the neural network, but it's safe for any neural network.
Yes.
Got it. Okay, thank you.
Thanks.
Yeah. Anyone have any questions? So yeah, I guess I have another question I had was just in terms of kind of the training time. So just to kind of get a sense, like, is the bottleneck typically the synthesis algorithm, the neural network training, or like where is the bottleneck during in like learning these programs?
So in learning these programs, the bottleneck is definitely the synthesis algorithm. One of the reasons is, of course, that the synthesis algorithms don't yet we don't have a way to really leverage GPUs for those. But aside from that, the synthesis algorithm is doing an enumerative search, and then it's doing an expensive parameter search, which doesn't have access to gradients, and that's definitely the bottleneck right now. Which is why also we are very excited about trying to adapt the near approach, which is something that we've so I can't find the slide for near, but basically the idea there is that you can look at smooth approximations of these programs and then use neural relaxations of these smooth programs to do this program search faster. And we showed that this learns very good programs in the supervised learning setting for animal behavior prediction. And now we are trying to adapt that to reinforcement, to this sort of reinforcement learning setting using the Propel framework.
So what are the obstacles for doing that adaptation?
So the main obstacle is that the domain-specific language there is assumed to be differentiable. We can get around this by using sort of smooth approximations of if-then else's and the other sort of non-smooth parts of our DSL. But that's the main thing. So we can't just plug and play it, because if you try and put any DSL into the near mechanism, it doesn't work. It tries to train things end to end, and so it assumes differentiability.
Mm-hmm.
Okay. Are there any other questions for Abhinav? Okay, so yeah, I guess thanks so much for taking the time to give this talk, Abhinav. And yeah, so we'll see everyone next month for the next neurosymbolic webinar. Hope to see you all there.
Thank you.
Bye.
Yeah, thanks. Actually, would it be possible for you to share your slides?
Sure.
Thanks.
Okay, thanks.
Cool stuff.
Thank you.